Good afternoon. Uh, Ahmad. I'm working in Professor Simmons Institute in Product and Bakery in Kathmandu. So, unfortunately, my another colleague is not here today because she is COVID positive. So, we too institute actually would like to take this course, but maybe from the next course or from the next lecture, she will be here. So let's introduce. So as I have told you, I'm Azad. You can call me Azad. So full name is Azad Kambakar, but feel free to call me Azad. And if we start from here,
Yeah, my name is Florian, and
so bachelor or master.
I'm still in bachelor, but I make master courses.
I'm Lucas. I'm now on the Master of Mechatronics.
I'm Michael. I'm doing this course as part of my master's specialization.
My name is Patrick, and I'm in the Master of Mechatronics.
My name is Florian, and I'm in the master of mechatronics.
So two followers so far.
My name is Daniel, and I'm also at the master.
Okay. So far, I know there are 10 people so far. But yeah. So Beck Kai, he's actually will be the tutor for this course. So if you need any kind of help, because we're gonna learn some tools in the whole course. So if you need any help, she will guide you through. And if you have any sort of questions, anything, write us on email. And yeah, it would be better if you write in English because most of the time you're gonna reply and his German is not good. So yeah. Okay. So far, have you introduced with model-based systems engineering, or this is the first time just you heard about model-based systems engineering? First time? Okay, but this really I would like to know because as far as I know about your level of understanding about model-based engineering, then I can deliver subsequently or relative to your understanding. So why did you take this course, any of you, randomly? Sounds cool? Or
Someone is in the waiting room of Zoom.
oh, I think he is here in the back. Okay, so model-based systems engineering is actually very, very new. It is not a discipline. I would say this is a sub-discipline of systems engineering. And have you heard about systems engineering so far?
A little bit.
A little bit. Very good. And have you took the course in the morning, Professor Simon?
Yes.
I think he also give you some understanding like what it is and yeah. Okay. So let's go to the presentation. Okay. So first of all, we'd like to know what we're gonna actually learn in the whole course. What's the goal of this course? So okay. So first of all, I understand in different way like how people understand. So my understanding of a course or when I try to learn something, I first try to know the thing, then understand the thing, and then I try to evaluate myself that can I really apply those things what I have learned and understood. right? So in the similar way, me and my colleague try to make the whole course that we can evaluate ourselves, like every student or every individual can evaluate. And in the whole course, we actually learned what is MBSE. So MBSE is the short form of Model-Based Systems Engineering, and then how to apply MBSE. So actually, to be honest, you can apply systems engineering, not model-based systems engineering, every possible way of your life. So you can apply it like, if you wanted to plan something for your breakfast, you can apply systems engineering. So this is very useful too, but we have to learn, we have to understand the core of this course. Then you can easily apply this thing into your daily life. And what are the challenges to deploy MBSE? So as I have told you in the very beginning, this is very young, I would say, discipline. As systems engineering is the main discipline, and this is a sub-discipline of systems engineering. So this whole discipline is not really flourished so much because there are some still laggings in this discipline because the whole thing is maybe you already heard about digital engineering. So this is also the sub part of digital engineering. So how you can actually make your whole thinking to product development through models, through digitalization of your product. So here there are some lags, and these lags, people are telling some lags, but I would say these are the very big lags because of those lags, you cannot really getting the utmost benefit of model-based systems engineering. So slowly we're gonna learn everything, what I had started here, these three particular things. And if you really understand these three things, I think I would say you understand pretty much 90% of model-based systems engineering because yes, please. So because in my last 4.5 years research, this is actually my understanding. Like, if you understand these three notions, pretty much almost 90% of the whole model-based systems engineering. So let's start. What is model-based systems engineering? So as I've told you, the learning curves. So we're gonna have 15 class, and if you see, like, no, we're gonna know things in different way, and you see the knowing part is getting higher here, and it will goes lower in end of the course, and the understanding is pretty much going some sort of middle, and then can. So I think in the very beginning you'll have no clue most of the time, but at the end, I personally observe that you can deploy something like you really understand the core of model-based systems engineering. And if we see this graph, I think it's pretty much understandable, like how the information flows goes from this level to the end, like from 0 level to the 15th level. And if I put this one, I think this is a little bit hard to understand, right? So if you try to understand from these two pictures, what is exactly the model-based systems engineering? So when you write something, it's really a little bit hard to understand, even though different people can interpret writings differently. But when you are expressing something with some figures, some photos or something, then people understand more clearly. So this is actually the goal of model-based systems engineering, because when we are making complex product or complex system, then it's really hard to understand the view of of the developers. Let's say, maybe, you know, if we are, I know you guys all are from mechatronics department, so mechatronics is the combination of software, electronics, and mechanical, you know, so to say. So you see, if you guys, you already know these three things, but when you are doing a complex systems engineering or, you know, design a complex system, then you have to come across with different engineers. So maybe some engineers, she or he has you know, understanding only with software. And when you are designing something and you try to explain the thing that she or he can run the code, maybe she will not understand because her understanding level is a little bit different than you, because she understand or he understand things from different perspective, from different views. So you see, if you express something to her with some sort of figures, you can clearly express your ideas, what you actually want from her or him. So, so this is actually kind of, we are doing kind of model-based systems engineering right now. So this is a very you know, raw things. People can interpret differently. I don't know this is what, but when I'm showing this, I think it has a different sort of overview. I think clear understanding, I would say this is a bit better. So, so this is the thing, but bear in your mind that up to the nth level, we will know exactly what is model-based systems engineering. Okay, so the first lecture objective, what is model-based systems engineering? So if we divided the model-based systems engineering, we find model-based, then systems, then engineering. So then I will come with the explanation in the next slide. Then what is the current status and the root of model-based systems engineering? So how much we have done, as I have told you, there are some challenges in model-based systems engineering so far. So, and where from actually it comes, and why actually people think that we need this new kind of engineering. And we'll have, I would say, 10-15 minutes discussion on the whole course structure, how we're gonna conduct the course and everything. Okay. So what is model-based systems engineering? So first, I think model-based systems engineering, if we want to understand the thing, then it's supposed to be systems engineering with models. So do you have, again, the same question, do you have any understanding of systems engineering? Any of you? Feel free, like, you know, I always try to feel more comfortable in the class, so you can feel one of your fellow mates. Just feel free to discuss, feel free to talk. No shy, no hesitation, okay? Any idea with systems engineering? No? Okay. So, okay, to give you the systems engineering idea, I think we can do some hands-on practice, right? What is this? Power puzzle. Yeah. So this is one part. Oh. This is battery, right? Let's put it here. Maybe battery covered. It does not make any sense with this, right? Let's see. And this is I think you understand this is what is this. So you see, so we will do systems engineering right now. So as an engineer, when you actually think of a system, so I think Professor Simon already gave you the inductive and deductive method, like how to think actually. It is actually called system thinking. So most of the time, like in systems, what's the difference? Actually, I think it's better to understand what's the difference between the systems engineering and other engineering disciplines. I would say in other engineering discipline, things are not conducted in a water. Let's say, when we are thinking, let's say you want to um, go to Vienna, let's say. So when you try to plan your journey, I think you have to take shower maybe, or then you need to take your clothes on. Then maybe you have to think like in advance that should I really take the train, bus, or my car? So if you are really environmental friendly people, think about sustainability, then maybe you will try to find some car sharing, or maybe there's, because always cost is a big matter in systems engineering, so because we wanted to reduce the cost in every way possible. So maybe if you find something that is cheaper and comfortable, and you're not making so much hassle to the environment, then maybe you will find something with car sharing, because also you need to go to faster. So you see your thinking patterns, and maybe let's say if you do not want to make your breakfast somewhere in the motorway, then you have to think about packing your breakfast as well, that you can have it on the car, or on the train. So this is actually the thing how and when you will think about your decision, about your problems. So we engineers or systems engineers normally tackle two different things during the product design or system design. So one more thing, like normally product and systems is same for me, but many lecturers or professors, they have a different view about product and systems, but for me both are same. So what we actually normally tackle, so we are calling this problem domain, and so problem domain, normally the solution is you wanted to reach safely to Vienna. So here you will take all the problems. Let's say, in the problem domain, you can think about the cost. Maybe then you can think about the comfort. Then maybe you think about, sorry?
Time.
Time, very good. Anything else?
Miscommunication.
Sustainability.
Very good. Miscommunication.
Like missing the train and something because of time management.
That I would not say miscommunication. I would say this is actually
Management.
yeah,
Time.
yeah, management would be right word. And the other one,
Sustainability.
sustainable. Very good.
Safety.
That's very good.
Flexibility.
Comfort, flexibility,
Yeah.
almost same. Yeah, so to say, these are the normal thing every designers, let's say, or even though when you're cooking, let's say, when you're preparing your dishes, you also need to think about this. And that's why, engineering is so interesting to me, especially because every time you have to tackle with the problem domain and or you have to fight with the problem domain and solution domain. So based on those criteria, we just making some solutions. So let's get back to the story to Vienna. So as a systems engineer, you have to divide the systems into different parts. So let's say every system has its subsystems, then it has components, then subcomponent, it has like, if you go to the molecular level, it can go up to that, but you should not go up to the molecular level because this is not our task. So as a systems engineer, we have to think, like how every single subsystem could accomplish one of your tasks or one of your function. So let's, yeah.
So is model-based systems engineering like you have to define requirements and then you have to find different ways.
Requirement is actually the next level, but before requirements, you have to identify the needs. So requirements is somehow, many people are telling that specification, system requirements, then design requirements. So it has different names. Or engineering requirements or engineering specification. So this is actually the last level when you really understand what you need. So what I actually try to make you understand, you see here, if you already know your problem domain, where you're gonna have the challenges, then you can decide smartly. So let's get back to the card. So when we are designing the thing, so let's say it has a function. As I told you before, function is a important thing because every subsystem, when you are calling something subsystem, so that's supposed to satisfy on function of the system. So let's say this one has the function. It is actually, I would not say this is a component. I would say this is a subsystem because it has some electronics inside. Because if I actually decoupled everything, then you will understand like systems engineering is really like a good way of thinking or a good way of understanding your problems or system problems. So let's say if we have this battery, let's put the battery in because we already know here we have to put the battery, but you have to design this. So this is what I'm showing right now. It is actually what we call the assembly, but assembly is not systems engineering. So you have to think back in your mind that this particular thing you have to design from the scratch. And how efficiently you can do it, that is actually the challenge of your, or that is the ultimate goal of systems engineering. Okay, so I'm just putting all together and you see, and it's work. So we define the function that is supposed to goes point A to point B, and this is actually working. So in systems engineering, you maybe one more example could be make more senses. Normally, when like any of you have done a coding course like Java or MATLAB or anything, there is a very common talks there that they're telling like think when you start coding, think about the smallest step. So what you can do, because you cannot really solve the whole problem in one shot, right? So you have to divide it. So this is actually called, maybe you have learned in the morning. This is called, let's say, if we are thinking of the system, then we should think of the subsystem, because we cannot deploy the whole thing in one shot. Then maybe component. I'll not go further. Okay, so so this is actually what we are doing here. This is called deduction as well. So different people, top down. Also, you can tell top down approach or deduction. And you find the up to component level. But you see, systems engineer supposed to think also in the back direction. And this is actually called induction or bottom up. So, you see, this is a little bit challenging because you have to think how to divide things, and you have to think at the same time how you're gonna join the things together and make the function works. So ultimately, systems engineering is actually this induction and deduction. So you have to think something, making a small and joining together and make it, functional. Then with models, because models is not there with systems engineering, that's why this is I think a historical talk, I would say, because systems engineering, when you wanted to deploy the systems engineering, you have to do many things in document based. So there is a clear distinction with document-based systems engineering and model-based systems engineering. So the traditional way of doing systems engineering is document-based. So you have to do some sort of thing, let's say in PowerPoint presentation or in Word or with some pen paper. But in model-based systems engineering, it has to be digitalized. It has the tool supposed to be, or the subsystem or the component, what you are thinking of, that has to be produced in digital form. So, and you have to integrate those as well, as I have told you. So induction and deduction again. And okay. And what do you think? What is actually a model? What is a model? I would like to know from every one of you, because model also very vague. It has different understanding to different people. What do you think, Florian? What is a model?
Mathematical description of my
Very good.
problem,
Okay.
physical problem.
Yeah, very good. I'd like to write it down, and you see, like it makes different definition or different understanding to different. So not write the whole thing. Yeah. For you?
Something which describes the functions of a
Very good.
certain thing.
Describe the function. Yes. Some kind of simplified, abstracted description. This is extremely good. So we can call it abstraction. Simplification. Please.
Maybe the basic requirements.
Basic requirements. For you?
Description of a real thing with words
Very good.
and forms.
Description of real system.
Maybe a sample system which describes the original system.
Yeah, this is pretty much both combination of these two. Abstraction or description of the real thing.
I would say like a combination of those things. It is a projection of the real world into a smaller or digital world.
Very good. Yeah, models. If you are really talking about model-based systems engineering, then digital world is the right word. But especially models can be anything. So for you,
A three-dimensional representation or something like that.
okay, here's another one. Okay, so to say, all the forms are more or less correct. Model is basically the abstraction of the real system. Let's say you wanted to do, or you wanted to design an aircraft. So you have to do, you cannot really, maybe in the simulation class, there will be one part with simulation. There I will show why we need actually model, and how we can save money. This you know already, but like the way I will show you, because I have some practical experience or practical examples, because we are also working for a startup, and there we have seen like how to save money, because in a startup it's always money is the biggest problem, and many good ideas died before born due to financial crisis. So in the startup, it is really very, very difficult to make decision because, as we have seen, those factors always you have to deal with. So there we're gonna see how the digital engineering actually help us. And yeah, so model is basically the abstraction or simplification. This is also very good of your real or physical product, physical system. So I think this thing is clear to everyone, right? If it is not clear, feel free. I can, make some other examples to make you guys clear. It's pretty much clear, right? Okay. So let's go to the. So I already described systems engineering. So now we have to understand what is systems. when we are calling something system, what is systems? Not systems, system. It is pretty much simple. Like let's say this one we can call system because it has a function. So when something is actually doing or fulfilling your requirements, come to you again. So when something is fulfilling your requirement, then, and there is actually the definition of functional and non-functional requirements. There will be a class of with this. So then we will have clear understanding on functional and non-functional. So this is a system, but this is not a complex system. And yeah, I think I would need another one lecture for describing the complex system and simple system. So I think this is not necessary for this course. So complex system normally, let's say a car could be a complex system, an aircraft could be a complex system. Why? Because different disciplines involved there, different domains involved there, and different stakeholders involved there. So combining all those things, managing all those things is really big task. Therefore, you know, complex system design or thinking of a complex system, we have to think in systematically, you know, and that's why we have to do systems engineering. So systems is something that actually fulfilling one or more functions. And engineering, I think this is, you do not know engineering explanation because we are doing engineering somehow. And we have talked a lot about the models. Okay, so can you see this? I don't think so, right? Okay, just to give you an overview about the systems engineering historical point of view, because systems engineering, it's not a new discipline, and it actually started. Sorry. Okay, so BC 385 to 323 is the starting of systems hypothesis. So system hypothesis actually first coined by Aristotle. You know Aristotle, right? So he was a great philosopher, engineer, scientist, inventor, whatsoever you can call him. So his proposition was the whole is greater than the sum of its parts. So here we have seen this is the whole, right? And the parts we have seen this is the part, right? So the function of this one greater than this function. This also has a function, right? So somehow it secure the batteries, right? So it has a function, but the total function is lower than like the total function is greater than this function, right? So this is actually very fundamental understanding, I would say, that he proposed. And there are many system hypotheses, and it's really interesting. So one more thing, I have all the references, and if you guys are really interested, then you can take the references as well. And it's quite too much for one course, and there are, I think, more than 15-20 books minimum 30, 40 publications. So, but if you wanted to know more, feel free to ask me. So then comes in 1928, system theory. And do you know who is the father of system theory? He's an Austrian guy. His name is, if I what do you call spell it correctly, Breton Alfie. He was a professor. I think he started in TU Wien, and from there he was some years in professor some technical university in Czech Republic, and then he went to USA. But it's like he has really like his one of his book is general system theory. It's called GST, and I think it's a really wonderful book. If you guys have time to understand the system, like he described human, because he is not the professor of engineering department. He was a biology professor, and he described the system so systematically. It was really wonderful, wonderful book. Then operation research. This is normally invented or instituted by the British scientists. Before the Second World War, they have actually problem doing complex engineering. So this is a mathematical way of who said math? You. So they actually think everything mathematically, and they try to make small solution first, then join this mathematical problem to that. So normally I do not read this much because I hate war, and yeah, but this is some kind of innovation for war. Then systems engineering. So it's from 1940, and it's basically proposed by the Bell Laboratory, and uh, they are somehow the pioneers. But the view of systems engineering actually is here with the Austrian guy. I think if you read the book, you will understand why I'm telling the real engineering is there. And after that, 1940 to 1960, they made another branch, system thinking. But honestly speaking, this is not a branch of another engineering discipline or something. This is somehow integrated with systems engineering, because as I have told you, like when you think top down or bottom up approach, then you need system thinking. And according to Professor Seman, everything is system thinking, because when you are doing engineering, you need to think of the problem domain, and then you execute the solution. So this is actually not a very important issue, but many scholars they try to describe system thinking as a different realm of systems engineering. And the model-based systems engineering. So, Florian, with your team, you told mathematics. The model is math, and the guy who actually proposed this model-based systems engineering, he is actually a mathematician. He's a professor of mathematics in MIT, and in 1993, he wrote a book on model-based systems engineering. He also had a book, I think 1976, he also had a book with systems engineering, something, I forgot the whole book name, but the first proposal came in 1993. This is somehow the whole pathway of model-based systems engineering. And it is not yet been flourished. And why I put 2006? Because international INCOSI. I forgot the full abbreviation. International. Oh, INCOSI. International. I forgot. I forgot. Maybe you can Google it. So INCOSI is the organization who are dealing with systems engineering, model-based systems engineering. They have every year symposium, publications, and many things. And if you wanted to be a systems engineer, they have some also possibilities. So they have, I think, 4 rank of in systems engineering certification. So you can Google it and you can find many information in that page. Okay. So 2006 actually INCOSI formed before, I think INCOSI formed 1990, and after that they were actually talking about making symposium and making discussion about systems engineering. And in 2006 they proposed actually model-based systems engineering, but the MIT professor, he actually proposed it in 1993. So that's why I just put two different here. Yeah. Okay. So any question here? No? Okay. Then types of system. As I have told you before, anything can be system. So it does not really make any sense for me to define different types of system. But I just put this slide to show you guys how different people actually think about system differently. So this is the guy, Austrian guy, Breton Olfi, 1968 in GTS. He actually described 2 types of system: open system and closed system. So if you have a look on the flux and the coffee cup, then you will understand what is actually open and what is actually closed. It is very explicit, but when we are gonna designing some system, then this simple description getting really very complicated. And from Kenneth Boulding, he considered, he is one of the earliest one also. He considered structure, clockworks, controls, open, lower organism, animals, man, social, transcendent. Like he also considered God as a system. Types of system according to Kenneth Boulding again. So in the 2 different books describing system differently. So natural and man-made, closed and open. So this one is more acceptable than this one. So this one, the old one. And Kante has more, I would say, engineering view of the system. So he is considering static, dynamic, stochastic, and deterministic, continuous, and discrete, open and closed, linear, and non-linear. Yeah, so this is actually types of systems. And next, we would like to see like what are the theories in systems engineering did. So we have to understand the system theories as well, because what actually system theories does, that is maybe a good question from your side. Normally systems engineering giving us some guideline to solve some sort of problem. So it is similar to, let's say the very famous theory of relativity, why we need to have that to have some solutions. So normally theory are using for making some solution of some problem. So this is called the modern theories of developments, that is proposed by Bernoulli, 1928 to 1933. Then organism and psycho and system theory, that is also again by proposed by Bernoulli. So forgive my alteration on Bernoulli because it's more Austrian or German word, no? Because I don't know, because this I try to utter it properly, but Professor Seman tell it differently than mine. Okay, so then maybe you heard about Shannon theory, and this is actually a very famous theory. This is considered one of the cornerstone of information technology, because how information will be exchanged, and this is basically Shannon wrote a master thesis, and I think he was a MIT student, and that time it was been considered that his master thesis is the most influential master thesis in the world so far. The number of master theses have been written down. So there are some nice videos on Shannon in YouTube. So he has a really marvelous life, and he has his way of thinking about systems and way of thinking about problems is really like very outstanding. So some sort of like Tesla. So I'm not talking about Tesla car. I'm talking about inventor Tesla. Okay. Then cybernetics. His name is BNR. He was also a professor on mathematics, I think, some of the university in USA, but I don't know. I cannot remember the university name. And cybernetics also very useful topic into system design world. And then general system theory in 1968, also proposed by Bernoulli, and there are many theories. Let's say chaos theory, then then another one is also very important to me. You also got Nobel Prize on this theory. Nash equilibrium, Nash theory, like win-win situation. And have you seen the movie? What is it called? Beautiful Mind. You should see this movie. Yeah, but it's a little bit funny to me, because this Nash theory's first part, actually it has two parts. Like when you're gonna make some decisions, you have to think in two different ways. So let's say if you have a partner, so both will win other than one will win. So how do you confirm that both will win? So this is the kind of philosophical game, and it is also known as game theory. Um, the first part actually proposed by another mathematician from Hungary. I forgot his name also. So, and the second part, the win-win situation or game theory, second part is actually proposed by Nash. And because of this theory, he got, I think 90, 50 or 60s, he got the Nobel Prize. And he died as a, what do you call, crazy man. Okay. So historical derivatives of scholastic activities. So how many publications are being published and from what time it was started? So the first publication on systems engineering started published from 1945. Then graduate course started in Bell Lab in collaboration with MIT, 1948. Then 1950, the first proceeding or conference paper was published by Kelly. Then first systems engineering course on MIT started in 1940. So 1950. So here, this one is a graduate course, and this is a normal course on systems engineering. And in 1957, first journal article was been published by Eigenstrom. Then first book by Hull published 1962. 1993, as I have told you, the book Model-Based Systems Engineering, and the professor name is Waymore. And 1995, Model-Based Systems Engineering book published by NASA. Then INCOSY first published their book in 2015. Yeah, so this is the whole lot of things or research and academic things that's been done in this way. So this is historical derivation of, just a moment, systems engineering standard. So we need to when we design something, so we have to follow some sort of standard. So, like in software engineering, IEEE has some standard. Then ISO has some standards. So these are the standards. MIL, sorry. Then 1974, there is another updated version of MIL for 1990. Then 1979 field manual. This field manual is basically for the defense use. Then ANSI and AIAA also have some guidelines. Then MIL standard. So this is MIL is military standard, 1994. Then IEEE 1220, 1998, 2002 ISO, ISO, IEC, IEEE, because before they have different ISO, IEC, and IEEE, they have different method or different guidelines. So they combine and make one guideline. And in 2003, ANSI and EIA, they made another one. So ISO again with IEC and IEEE, they made another guideline in 2016 so far. So but this is all related to systems engineering. So far, to the best of my knowledge, there is no standard for model-based systems engineering, and we people are some more or less suffering because of the lack of standard. Because you know, to make something digitally, one tool to another tool, data exchange supposed to be happen. That is not really possible with the current situation. So let's say if you design something in SysML, and if you design something in 3D CAD, you cannot really exchange the data. And you know, like when you cannot change information, the system actually, it means the digital system is not working. But physically it's possible, but not in digitally. Okay. So system hypothesis, what I was actually discussing before, system hypothesis actually, the Aristotle thing is all things have several parts and the whole is different from its parts, which is the fundamental understanding of systems. Then system theory, it's actually everything. Let's say Fourier transformation is also system theory. Game theory also system theory. So when you are designing a system and some sort of theory you need to accomplish your system, then it will be called system theory. So there is a misunderstanding in our realm most of the time when we are talking with the scholars, like they meant something else with system theory, but it is like they meant something like, you know, the GTS is a system theory, then I don't know, then the game theory is a system theory, but Fourier transformation maybe not a system theory because it has different use cases. So my understanding is when you are designing a system and if you need a system theory for deploying your solution, it is called system theory. Operation research, I have discussed in the previous slides. What is it? Then systems engineering is an interdisciplinary approach. So this is more what we call academic way of explaining systems engineering, but we have discussed already. And we have seen the main focus is customer needs, requirement engineering, design synthesis, and verification and validation. And system thinking, I also described this thing before. System thinking is like thinking of system, anything. When you're designing a system, anything is system thinking. Okay. This is just to give you some overview about the systems engineering or model-based systems engineering approach and how far we have gone and how many projects so far accomplished. So this is BC 3200 to 1100 water distribution and irrigation. It was kind of systems engineering approach. Then pyramid system, many people consider because they have small parts and they you know, bring it together and they made a specific shape, and that is also a systems engineering approach, which was BC 2600. Then Roman road system, that is also systems engineering approach, and this very generic explanation or graphical representation here, but if you read or search in Google with those keywords, you will find the background of system thinking that, you know, the ancient people also knew how to do systems engineering. So this is not a new thing, but we're learning new, and you know, everything has been digitalized and our need has been changed so far. So we need to learn it in a new way to meet our new requirements. Then NIC missile system 1945 to 1953 that has been also deployed through systems engineering approach. Then Sage air defense system, also systems engineering. Atlas ballistic missile system. Oh my God, I'm sorry. So many weapon examples as a systems engineering approach. Then X-Rim project. This is the first one actually conducted by NASA, and this is a satellite. I think it is related with X-ray something. Um, and this whole project they deployed. They started 2018, and they are telling that they will finish by 2022. I do not have any news up to now that they have finished or they deployed or they finished the project or not. So far, maybe from here, the another one is AeroCube 10, 2019. This is also a NASA project, and they are telling that they have finished this project with systems engineering approach, model-based systems engineering approach. So you see, this is the only project that's been finished so far with real model-based systems engineering. And today we are here to learn this thing, model-based systems engineering, and it is not really so easy. It is quite difficult due to the tool problems, but in terms of understanding, I would say it is pretty much explicit to the scholars and to the engineers or to the different disciplines. Okay, so this is a little bit clear view of system, like how you understand this is a system. So system of systems. So now let's talk about first system. So as I shown you that, you know, system, subsystem, module, and component. So I think you guys are pretty much familiar with the modular design, right? And you see, when you try to think of a module, you have to think, you know, in systematic order. And this was actually one of the biggest quest when I started systems engineering and I started the startup works. And I was thinking like I would like to deploy everything for the startup modular thinking, you know. I really didn't understand how I could make a module. It is explicit from the definition context. What is actually a module, you know? But when you try to design something, it is really hard to say subsystem is a module or this one or component would be a module. It's really very hard. So what do you think? Like, you know, if I make a component and I think this is a module of my system, is this right? Or a subsystem could be a module of my system is the right one. So what is your understanding? So the thing is, there is no clear guideline for that. it is, if you tell that my component is my modular design, or this is a one module of my system, that is also right. And if my subsystem is the module of my system, that is also right. But my preferable way, like your module supposed to help to your main system to fulfill the whole function of the system. So what is systems of system? With the pictures, does that make any sense? Please.
System of system that is integrated inside a system. So like an aircraft, it's a system itself inside another system, just like hydraulic system and stuff.
Now, the system of system is a little bit different. System of system is like is the environment of your system. Where, let's say, the airport, the road, because when you are going to the airport, you are going to a road. You need to take a bike or car or train whatsoever, and you are using the environment. So this is actually the system of system. So system of system is pretty much very close to the system environment, because where the system will it's already done. No, we have time, right? Okay, sorry. Okay, and system boundary is like this red color. This is basically a system boundary. So now we try to understand if we consider a aircraft, this is a system, right? And when we are thinking of the subsystem, it will have many subsystems. So one aircraft has engines, avionics systems, then landing gear. And you see, this landing gear is a subsystem, but the module is something else. The shock absorber is the module. So it actually helps to fulfilling the subsystems function. So modular design, when you will think of modular design, I think from this time, the modular design will be much more clearer to you. And the component is both. So here another thing is like normally when we are design a system, we have to think of 3-4 things, like the system context. It is like the data, signals, materials, energy, and activities. So what your system actually come across during its life cycle. So and of course there is an operator of your system. So when you are designing the operational concept of your system, then you have to think of the operator. It could be human, it could be machine, whatsoever. Yeah, so far, this is actually the whole lecture for this evening. And do you have any questions in this front? Or are you feeling bored a little bit? Hearing system every time, system, yeah, system. or any kind of confusion, anything? So I would like to give you a small task before coming to the next class, because the objective of this class, you have to learn the model-based systems engineering. So every individual like um, consider a flying vehicle. Any of you? Like, like every individual flying vehicle, I'm not naming it. So it could be flying car, it could be small aircraft, it could be big aircraft, it could be fighter aircraft. And take it as an example and just show in one page with graphical representation how you actually think of a system. And from my point of view, this is a 10-minute task. If you use your 10 minutes, it could be finished. So just that will, there's also a system thinking. So how you gonna think of a system, and how you actually think of the problem domain and solution domain, during the systems engineering. So next class will have a, I think, greater view, because now I'm actually giving lecture. So if you can remember the first one, that no, so this is what I know. So maybe today I gave the lecture, and maybe you know today about the model-based systems engineering. And when you practice a little bit at home and thinking about it, then I think it will give you a more clear understanding on model-based systems engineering. So the key thing is, in model-based systems engineering, we have to think based on model. We have to do systems engineering based on model. So here we are not talking about digital model. You can maybe make a sketch and show your way of doing engineering. There is no right or wrong. Honestly, there is no right or wrong. I am requesting you to do that because then we'll have some scope of discussion.
Do we have to upload it to Moodle or just
Bring it into the class. We'll discuss. This is not a exam part. So this is only the understanding. And I think when you understand this thing, then you can easily do the assignments. There will be 3 or 4 assignments, and if you understand the logic behind, then I think the assignment will not be so difficult. Okay, so let me stop here. And